Let me tell you a story which will become your foundation for understanding how Linux memory management works, both in real and virtual world. Meet John, a genius coder studying at a top university. But life is not easy. He lives in a tiny apartment, rent is high, space is limited. But John's dreams are big. A huge mansion, a car, and everything he can't afford in real life. So using his coding skills, he builds his own metaverse, a virtual world that looks unlimited. But how does John move between his real apartment and his virtual world? He builds a special device, a VR headset that connects both worlds. Remember this, inside his virtual world, each luxury item, the house, bike, or car, is a virtual asset. But behind the scenes, each one connects to John's real apartment. A few days later, Jason, another student from the same village, joins John. He's poor too, and now they share the same small apartment. But John gives Jason his own virtual world in the metaverse. The two even meet in a shared cafe. Let's step out of the story and look at what this really represents. Here, John's and Jason's apartment will become our physical memory, RAM. Virtual world will become virtual memory. VR headset, which they both used to move from real world to virtual world, which acted as a translator, will become our page table. Don't worry, I will explain page table going further. In the real world, physical memory is not one huge chunk. It is divided into many small fixed size blocks called pages. That's why in everything we show next, we'll talk in terms of pages and their numbers. Each physical block is called a page frame and has a unique index called a page frame number. Here on top, we have process X, John, and his virtual memory space. Inside that box, you see VPFN0, VPFN1, VPFN2, and so on. Each VPFN is a virtual page. Think of them as a virtual assets in John's metaverse. VPFN0 might be his mansion, VPFN1 his bike, VPFN2 his sports car. Remember, these are virtual. They are references in John's world, not physical memory yet. When John's program accesses a virtual page, for example VPFN2, the car, the system must figure out where in real RAM the car's data actually lives. That translation is performed by the page table, which we show just below the virtual space. If you remember, in our story, John uses his VR headset to travel from real world to virtual world, which in our computer world is the page table. The page table acts like a translator. Every time John tries to access something in his virtual world, say VPN0, the page table figures out where that really exists inside the small apartment. I mean, the physical RAM. And this is Jason's virtual memory space. Just like John's, he believes he has his own complete metaverse. Both of them, John and Jason, live in different virtual worlds, but in reality, they are sharing the same physical apartment, the same RAM. If you recall, Jason and John can meet each other in a shared cafe in virtual world. That's how shared memory works. Multiple processes can map to the same physical frame while still thinking it's their own. So, to summarize this diagram, each process gets its own virtual memory space, isolated and private. The page table translates the virtual page to a physical page frame. The physical memory or RAM is limited and shared among all processes. So in short, John and Jason may live in their own separate metaverses, but behind the scenes, both their workloads are carefully mapped onto the same real limited RAM, thanks to the magic of virtual memory and page tables. So next time an interviewer asks you, Can an application directly access the physical RAM? The answer is no. Every process only sees its own virtual memory, which is mapped to physical memory through the page table. Let's see some action. Let's first check how much memory my system actually has. So I run grep memtotal/proc/meminfo. It shows memtotal as 3490164 KB. So I've got around 3.4 GB of RAM available on this machine. Now let's find out what the page size is. So I run getconf page_size. Oh, it shows 4096. But wait, who decides the size of these pages? The size of each page is determined by the system's architecture. For example, in a 64-bit system, the page size is typically 4 KB, though large pages like 2 MB or 1 GB also exist. Let me check my system's architecture using command uname-a. You can see it's a 64-bit architecture, and that's why we are seeing 4 KB pages here. Now let's create a simple process for JSON with sleep 1000 and PID equals to $! This command will run sleep 1000 in the background, stores its process ID in the variable, and then prints that PID. Let's peek into his virtual world using proc PID maps. What we are seeing here are virtual memory regions, JSON's view of memory. Every process in Linux lives in its own virtual memory space, isolated from everyone else. We just saw how it works, but why does memory management work this way? Because RAM is limited and expensive. Since the early computing days, programs wanted more memory than the system could physically provide. So operating systems developed virtual memory, a smart illusion. With it, each process feels like it has its own giant memory. The OS can reuse physical memory frames efficiently. We can even swap out rarely used pages to disk. It gives security, isolation. One process cannot read another's memory directly. It also enables shared libraries, saving space when multiple apps use the same code. This design lets our small 3 GB RAM feels like an endless world to multiple processes at once. Where will you see this in action? On any Linux system or even on a Kubernetes node, if you run the top command, you'll notice 2 columns. Virt, V-I-R-T, that is JSON's virtual world, the total memory space a process thinks it owns. RES, what's actually mapped to physical RAM, JSON's real pages in memory. So when you see high virt but small RES, it means most of JSON's world exists only virtually. But when RES grows, he's actually consuming real RAM on the node. Before you learn from anyone, always check their credibility. You can verify mine on LinkedIn. Our mission is to teach practical concepts on technologies listed on screen, making you ready for both interviews and real-time troubleshooting. For more information, check the description below.